Want to deploy scalable applications on AWS without worrying about managing servers? Meet Amazon ECS, the easiest way to run and scale Docker containers in the cloud. In this series, I'll take you from beginner to advanced, covering everything you need to know about ECS, from the basics to deploying full-stack applications with autoscaling, load balancing, and CI/CD pipelines. By the end of this series, you'll have hands-on experience and the confidence to deploy a production-ready full-stack application on AWS ECS. Before we dive into the video, if you find this content helpful, be sure to like, subscribe, and hit the bell icon so you never miss any upcoming videos. Before AWS ECS, deploying containers on AWS was a completely manual process. Let's walk through what it used to look like. First, we need a virtual machine to run our application. This is like renting a computer in the cloud. Next, we install Docker on the EC2 instance. Docker helps us run applications inside lightweight, isolated environments called containers. Then, we download the application's container image from a container registry like Docker Hub or Amazon ECR. This image contains everything needed to run the app. Once we had our Docker images, the next step was to run our containers. But running a single container was just the beginning. Real-world applications often needed multiple containers working together. We could start a container using a simple Docker run command, but managing multiple containers manually quickly became complex. To simplify this, we could use Docker Compose, which allowed us to define multiple containers and their configurations in a single file. With just one command, we could spin up an entire environment. For production, we needed an orchestration tool like Docker Swarm, which allowed us to deploy and manage containers across multiple EC2 instances. This diagram illustrates the architecture of a traditional container deployment on AWS, showcasing the key components and their interactions. While deploying containers manually on AWS using EC2 works, it comes with several challenges that make it difficult to scale and manage efficiently. Too much manual work. Setting up and managing servers for containers takes a lot of effort. You need to create, configure, and maintain instances, which is time-consuming. Hard to connect services. Containers need to talk to each other, but setting up networking, load balancing, and service discovery manually can be tricky. Difficult to manage containers. You must manually decide where to run containers, restart failed ones, and scale them when traffic increases. It's a lot to handle. Security risks. You need to ensure only authorized users access your containers, protect sensitive data, and meet security standards. Doing this manually is challenging. Slow and complicated deployments. Manually building, pushing, and deploying new container versions slows down development and increases the risk of errors. ECS solves all of these problems by automating infrastructure, networking, scaling, security, and deployments. Infrastructure automation. With ECS, you don't have to create and manage EC2 instances manually. If you use AWS Fargate, you don't even need to think about servers at all. AWS runs everything for you. Easy networking and service discovery. ECS automatically sets up networking so containers can talk to each other. It also integrates with a load balancer to distribute traffic between multiple containers. Automatic scaling. ECS automatically scale up during high traffic and scale down during low traffic to save costs. Built-in security. ECS handles security by giving each container the right level of access using IAM roles, securing sensitive data with AWS Secrets Manager, and keeping logs for compliance. Faster deployments and updates. ECS works with AWS Code Pipeline, making it easy to deploy new versions of your app automatically. You can also use rolling updates or blue-green deployments to avoid downtime. This diagram illustrates the architecture of a containerized application deployed on AWS ECS, highlighting the key components and how they interact to ensure efficient container management and scalability. Now, let's talk about the key concepts in Amazon ECS. Understanding these fundamentals will help you grasp how ECS works and how to use it effectively. ECS Launch Types. How your containers run on AWS infrastructure and who manages the underlying servers. ECS Components. the essential building blocks of ECS, like clusters, tasks, and services. ECS Autoscaling. How ECS automatically scales your applications up or down based on demand. ECS Networking. How containers communicate with each other and external services using AWS networking options. ECS Monitoring and Insights. Tools like CloudWatch and AWS X-Ray to track performance and troubleshoot issues. ECS Security. Best practices for securing your ECS workloads with IAM roles, security groups, and task permissions. ECS Deployment. Different ways to deploy and update your applications in ECS. ECS Storage. How containers manage and persist data using EBS, EFS, or Fargate ephemeral storage. In the next sections of this video, we'll dive deeper into each of these topics, breaking them down step by step so you can understand how they work and how to use them effectively. Let's talk about ECS Launch Types. A launch type in ECS defines how your containers run on AWS infrastructure. It also determines who is responsible for managing the servers, you or AWS. There are three types of launch options in ECS. EC2 launch type, Fargate launch type, and on-premises servers. In EC2 launch type, you provide and manage the servers where your containers run. You control everything, including scaling and updates. ECS schedules tasks on EC2 instances that you provision inside an auto-scaling group. With Fargate launch type, AWS does all the heavy lifting. You don't need to manage servers, just define CPU and memory for the task, and AWS handles scaling, networking, and security. Fargate still uses EC2 under the hood, but you never see it. AWS dynamically provisions and manages the EC2 instances for you. So, you get all the power of EC2, without any of the maintenance. With Amazon ECS Anywhere, you're no longer limited to running containers just on AWS. It allows you to register external instances, like on-premises servers or virtual machines, directly to your ECS cluster. This means you can manage and scale your containerized applications seamlessly, whether they are in the cloud, on-premises, or a hybrid environment. Now, let's dive into how an EC2 instance runs on real-world hardware to give you a clear picture of what's happening behind the scenes. AWS data centers, the physical layer. AWS operates massive data centers filled with racks of powerful physical servers. These servers are interconnected with high-speed networking to ensure low latency and high availability. To enhance reliability, AWS organizes them into availability zones within different regions, providing redundancy and fault tolerance in case of failures. When you launch an EC2 instance, AWS runs it on this powerful physical server inside massive data centers worldwide. AWS Nitro Hypervisor, the virtualization layer. AWS uses a specialized Nitro hypervisor to efficiently create and manage multiple virtual machines on each physical server. When you launch an EC2 instance, it becomes one of these VMs, receiving dedicated virtual CPU, memory, and disk space. The Nitro hypervisor ensures secure isolation between instances, allowing AWS to run multiple EC2 instances on a single physical machine while keeping workloads separate and secure. EC2 instance creation. When you launch an EC2 instance, AWS follows these steps behind the scenes. AWS selects a physical server in your chosen availability zone. The Nitro hypervisor creates a virtual machine with the CPU, RAM, and storage you specified. The VM boots up using an Amazon machine image, which contains your operating system. AWS assigns your instance a virtual disk for storage and a network interface for communication. This process happens within seconds, providing you with a ready-to-use virtual server on AWS infrastructure. Networking and security. Once your EC2 instance is up and running, AWS takes care of networking and security. The EC2 instance is placed inside a virtual private cloud, which acts like a private network for your resources. You configure security groups, firewalls, and IAM roles to control who and what can access your instance. If needed, AWS assigns a public IP address so your instance can communicate over the internet. This setup ensures your instance is secure, isolated, and connected as per your requirements. Running and scaling your EC2 instance. Your EC2 instance is now up and running. You can use SSH or RDP to access and manage your instance. Install software, set up services, and configure it to meet your needs. Manually add more instances or use auto-scaling groups to adjust capacity automatically based on demand. With EC2, you have full control over your virtual machine, just like a traditional server, but with the flexibility and scalability of the cloud. Now, let's dive into how AWS Fargate actually runs behind the scenes. AWS Data Centers, the physical layer. AWS Nitro Hypervisor, the virtualization layer. Even though Fargate is serverless for users, meaning you don't have to manage or provision any servers, AWS still needs physical infrastructure to run your containers. Similar to EC2 instances, AWS Fargate also runs on AWS data centers using AWS Managed Virtualization. You simply define the CPU and memory requirements for your containers, and AWS automatically provisions the necessary compute resources behind the scenes. Fargate Compute Fleet and Firecracker Microvirtual Machines. When your Fargate task launches, AWS works its serverless magic behind the scenes. Instead of standard EC2 instances, it provisions resources from a specialized Fargate fleet using Firecracker Microvirtual Machines, the same lightweight virtualization technology that powers AWS Lambda. Each task runs in its own isolated environment, preloaded with Docker and the ECS agent for instant container startup. AWS dynamically allocates just the virtual CPU and memory you specify, completely abstracting away the underlying infrastructure. Networking and security. Fargate delivers built-in security through complete task isolation. Each runs in its own Firecracker micro VM with a dedicated network namespace, just like a standalone machine. AWS adds multiple protection layers, IAM controls access, VPCs isolate traffic, and security groups filter connections. You get VM-level security with container agility, all managed automatically by AWS. Running and scaling. Fargate automatically deploys your tasks across AWS's managed infrastructure. Unlike traditional EC2, you never control the underlying servers. AWS handles all placement across their optimized VM fleet in your chosen region. While you can't specify exact locations, AWS ensures intelligent scheduling for maximum availability and efficiency behind the scenes. Now that we have a basic understanding of Amazon ECS, let's break down its 4 core components that work together to manage containerized applications efficiently. Cluster, service, task, and task definition. Whether you are running containers on EC2 instances or using AWS Fargate for serverless execution, these components form the backbone of ECS, allowing you to focus on your application logic rather than worrying about infrastructure management. A cluster is a logical grouping of resources where your containers run. Think of it as a workspace that organizes and manages your containerized applications. If using EC2 launch type, the cluster consists of EC2 instances registered to ECS. These instances run the ECS agent, which allows ECS to manage them. If using Fargate launch type, AWS handles the infrastructure, and you don't need to worry about EC2 instances at all. You can have multiple clusters for different environments. A service is responsible for maintaining a specified number of tasks running at all times. It automatically replaces failed tasks and integrates with a load balancer to distribute traffic. Ensures high availability by restarting failed tasks. Works with auto-scaling to adjust the number of running tasks based on demand. Supports rolling updates and zero downtime deployments by gradually replacing old tasks with new ones. A task is a running instance of a task definition. It can contain one or more containers that work together as a unit. Tasks are what actually run your application inside the ECS cluster. Each task has its own set of containers, storage, and network settings. You can run tasks independently or as part of a service. A task definition is like a recipe that tells ECS how to run a task. It includes configurations like container images, CPU and memory allocation, networking mode, environment variables, and IAM roles, logging and monitoring settings. So, how does these AWS ECS components work under the hood? Let's break it down step by step. First, you define how your container should run by creating a task definition. It specifies the Docker image, CPU and memory requirements, networking, and more. Next, you launch a task, which is simply a running instance of your container. If you need high availability, you can use an ECS service instead. It automatically manages multiple tasks, ensuring your app stays up and running. The tasks run inside an ECS cluster, which is a logical grouping of resources using either EC2 instances or Fargate. If you're using a service, ECS constantly monitors your tasks. If one fails, it spins up a replacement automatically, keeping your app resilient. Finally, to distribute traffic evenly across your tasks, you can integrate an application load balancer. It routes requests to healthy containers, ensuring smooth performance for your users. Now let's talk about ECS Autoscaling. In ECS, autoscaling operates at the task level, meaning your containers scale horizontally by adding or removing identical task replicas. Each task must have clearly defined resource limits, CPU shares, memory reservations, network bandwidth allocation, and storage IOPS when using EC2 launch type. These limits are crucial because they determine how AWS places and scales your tasks across the underlying infrastructure, whether that's your EC2 instances or Fargate capacity. ECS provides three sophisticated scaling approaches. Target tracking is the set it and forget it option. Just pick a metric like CPU usage, set your target value, and ECS automatically adjusts tasks to maintain it. Perfect for hands-off scaling. Step scaling lets you define exact rules, for example, adding 2 tasks when CPU exceeds 70% or 4 tasks when it hits 85%. Scheduled scaling lets you anticipate regular patterns, like boosting capacity before your daily analytics jobs run or scaling down overnight. The real power comes when combining these methods. Imagine your service handling a sudden viral traffic spike. Target tracking would react immediately, step scaling would provide larger adjustments if the surge continues, while scheduled scaling prepares for known busy periods. Networking is the backbone of any containerized architecture. Whether you're using EC2 or Fargate launch types, Amazon ECS provides powerful tools to manage connectivity, discovery, and security. Let's break down 3 critical concepts and how they work across both deployment models. ECS supports 4 network modes, but their availability depends on your launch type. Bridge network mode is the traditional Docker networking model where containers do not receive unique externally routable IP addresses. Instead, they share the EC2 instance's IP and connect to a virtual network bridge. Each container gets a private IP within the bridge network, but to communicate externally, they must use network address translation. Since all containers on the host share the EC2 instance's IP, port mapping is required, meaning you must manually map container ports to available host ports to prevent port conflicts. While this mode is lightweight and Docker native, it introduces port collision risks and NAT overhead, making it best suited for legacy applications or simple test environments rather than large-scale, modern deployments. In host network mode, containers bypass Docker's virtual networking entirely and connect directly to the EC2 instance's network interface. This means that instead of getting their own private IP addresses, containers share the host's IP address and ports. Because there is no network address translation, network packets flow directly between the container and external services. This eliminates the networking overhead seen in other modes, making it ideal for applications that demand high performance and low latency. However, there's a trade-off. Since containers share the host's IP and port space, there is no isolation between them. This means port conflicts can occur if multiple containers attempt to bind to the same port. Security risks increase because all containers can see and use the same network stack. In AWS VPC mode, each ECS task gets its own elastic network interface directly from your Amazon VPC. That means every task behaves like a separate virtual machine on your network, with its own private IP address. This is very different from bridge or host modes, where containers share the EC2 instance's IP. Because every task has its own ENI, security becomes much better. You can attach individual security groups to each task, just like you do for an EC2 instance. This allows you to control who can access which task, at the network level. Service discovery becomes easier. Since each task has a unique IP inside your VPC, other services can easily find and communicate with it. Network performance is predictable. There is no NAT or port mapping involved. Tasks communicate directly over the VPC network, ensuring low latency and high throughput. This is why AWS VPC mode is the default and recommended network mode for production workloads, both on EC2 Launch Type and Fargate Launch Type. In None mode, ECS tasks do not get any network interface or IP address at all. This means they cannot send or receive any network traffic, no internet access, no communication with other containers, and no connection to external services. Primarily used for specialized workloads like batch processing or security-sensitive operations where network access must be intentionally disabled. Containers can only communicate through shared volumes or inter-process communication mechanisms. ECS Service Connect is a built-in service discovery and networking feature that simplifies how containerized services communicate within your ECS clusters. In modern applications, services need to communicate, like a front-end talking to a back-end API. Traditionally, managing these connections requires load balancers, DNS configurations, and manual networking rules, making it complex. ECS Service Connect simplifies this by automating networking, traffic routing, and security within Amazon ECS. It allows services to discover and communicate using simple names without worrying about changing IPs or complex setups. It offers built-in observability for monitoring and troubleshooting. With better reliability, easier networking, and secure communication, ECS Service Connect lets you focus on building your app instead of managing infrastructure. Let's see how Service Connect works. When you deploy a task, like a backend API, you give it a logical name, for example, cart service. This name remains the same even if the underlying containers change, making communication between services easier and more reliable. Service Connect maintains a live directory of all running services. When the frontend needs to talk to cart service, it doesn't need to know the IP of the cart service. Service Connect automatically finds and routes the request. An Envoy proxy, automatically deployed with your tasks, acts as a smart router. It balances traffic between multiple instances of cart service. Handles failures by retrying requests to healthy tasks. Encrypts traffic if TLS is enabled for secure communication. In a distributed architecture, services often run in different AWS accounts or VPCs. Traditionally, making them talk to each other required setting up VPC peering, transit gateways, or complex routing rules. But with ECS Service Connect, this process becomes much simpler and more secure. Service Connect allows ECS services to communicate across different VPCs and AWS accounts without requiring public exposure or manual networking configurations. It uses AWS's secure infrastructure to automatically route traffic between services, maintaining high performance and security. With ECS Service Connect, you can enable transport layer security encryption for service-to-service communication, ensuring that all data exchanged between services is encrypted in transit. This means that even if traffic is intercepted, it remains secure and unreadable to unauthorized parties. TLS prevents data interception, protecting against man-in-the-middle attacks. Even if someone tries to intercept the traffic, the encrypted data remains unreadable. Only trusted services can communicate with each other. Mutual TLS ensures that both the sender and receiver verify each other's identity before exchanging any data. TLS management is simplified. With ECS Service Connect, AWS takes care of the certificates and encryption, so you don't have to manually configure and maintain them. By enabling TLS in ECS Service Connect, you get a secure, reliable, and hassle-free way to protect your service-to-service communication, allowing you to focus on building great applications. Now let's talk about monitoring and insights in ECS. AWS Native Monitoring Tools. For basic visibility, AWS provides built-in tools to monitor your ECS clusters. Amazon CloudWatch collects essential metrics like CPU and memory usage at the task level, letting you set alarms for thresholds. CloudWatch Container Insights takes this further with pre-configured dashboards that visualize performance trends, errors, and resource bottlenecks across clusters. Meanwhile, ECS Event Streams gives real-time updates on task state changes, such as deployments, failures, or scaling events, helping you track cluster activity without manual checks. OpenTelemetry for unified observability. While AWS tools cover infrastructure metrics, OpenTelemetry provides deeper, application-level insights. It automatically captures metrics, logs, and traces in a single framework, correlating data across microservices. With the AWS distro for OpenTelemetry, you can deploy OpenTelemetry collectors as ECS sidecars to instrument apps without code changes. Traces show request flows between services, while structured logs include task metadata for faster debugging. Combining AWS tools with OpenTelemetry eliminates blind spots. CloudWatch ensures cluster health, while OpenTelemetry reveals how applications behave inside containers. Together, they help you optimize costs, troubleshoot faster, and maintain reliable ECS workloads, whether using Fargate or EC2. Container security in Amazon ECS requires different considerations depending on whether you use the EC2 or Fargate launch type, but both share common security principles. Securing the infrastructure layer is essential to maintaining a safe and resilient ECS deployment, especially when running containers on EC2 instances. When using the EC2 launch type, you're responsible for securing the underlying virtual machines that run your ECS tasks. This introduces several areas you must actively manage. Operating system hardening. Regularly patch the host OS and Docker daemon to fix known vulnerabilities. Use a minimal, hardened AMI and remove unnecessary software packages. Disable unused ports and services. Only expose the ports and services that are absolutely necessary. Configure IP tables or security groups to block inbound access to unneeded ports. Use Instance Metadata Service version 2. Enforce the use of Instance Metadata Service version 2 to prevent SSRF-style attacks that could leak sensitive metadata like IAM credentials. This adds an extra layer of protection by requiring session-based tokens. Docker daemon security. Lock down access to the Docker daemon socket. Unprotected access to this can lead to full host compromise. Network mode awareness. If you're using bridge or host network modes, be aware that containers may share the network namespace or stack of the EC2 host. This means a compromised container could impact the host or other containers if additional isolation isn't in place. Limit container-to-container communication using security groups and IP tables rules, and consider using AppArmor or SE Linux for added isolation. Fargate abstracts the entire infrastructure layer, so you don't manage or patch any EC2 instances. However, that doesn't mean there are no security considerations. AWS handles the host OS. Fargate automatically manages the operating system and Docker runtime updates, drastically reducing your operational overhead and patching responsibilities. Task isolation. Each task in Fargate runs in its own lightweight VM, which provides stronger security isolation than EC2 tasks running on the same host. No matter which launch type you use, you can boost your container-level security by using the AWS VPC network mode. This gives each task its own elastic network interface and private IP address within your VPC. Identity and access management. Identity and access management plays a vital role in securing ECS deployments, regardless of whether you're using the EC2 or Fargate launch type. It ensures that your tasks and services only have access to the AWS resources they truly need, and nothing more. Instead of embedding long-term credentials like access keys into your container images or environment variables, ECS tasks should assume IAM roles. This follows the principle of least privilege, meaning each task only gets the minimum permissions required to function. This significantly reduces the blast radius in case of a security breach. For EC2-based ECS tasks, permissions are provided via the EC2 instance profile role. This role is assumed by the ECS container agent running on the EC2 instance. It's critical to ensure that this role only grants minimal access needed for ECS operations, such as pulling images from ECR or sending logs to CloudWatch. Fargate makes this process more streamlined by allowing each individual task to be assigned a task role, completely removing dependency on the underlying infrastructure. This improves security and flexibility, as different tasks can have different permission sets even when running on the same Fargate host. Regularly auditing IAM roles and policies is essential to prevent permission creep. Over time, ECS task roles or instance profiles can accumulate excessive permissions, increasing the risk of unauthorized access. Review and tighten these roles periodically to ensure each task or service has only the minimum permissions required. This helps maintain a secure ECS environment and supports the principle of least privilege. Implement resource-based policies for services like Amazon ECR to tightly control access. This lets you define exactly which IAM roles or users can push or pull container images, reducing the risk of unauthorized changes. Additionally, enable AWS CloudTrail logging to capture all ECS API activity across your account, which helps detect unusual patterns, unauthorized access attempts, or misconfigurations in real time. Managing secrets, like API keys, database passwords, and encryption keys, is one of the most critical aspects of securing your ECS workloads. Because containers are short-lived and may scale dynamically, you need a robust strategy that avoids hardcoding or insecure storage of sensitive data. Never store secrets directly in task definitions. These are visible in plaintext in the ECS console and APIs. Environment variables. These can be exposed through logs, crash reports, and CloudWatch debugging. Docker files or container images. If you push an image to a registry with secrets inside, anyone with image access can read them. Any developer, admin, or attacker with access to ECS task definitions or ECR can potentially extract these secrets. Instead of hardcoding, store your secrets securely using AWS Secrets Manager. Designed specifically for storing sensitive data like passwords, tokens, and certificates. AWS Systems Manager Parameter Store. Good for storing configuration values and simple secrets. Avoid caching secrets on the host. Make sure your application doesn't write secrets to disk or store them in temporary files. Control access to instance roles. Limit the permissions of the EC2 instance profile so it can't access more secrets than necessary. Use Instance Metadata Service version 2 to protect the instance metadata and avoid secret leakage through SSRF. Let's break down how to secure EC2 and Fargate workloads while they are running. With EC2, you're responsible for both host and container security. Start with Amazon Inspector, which automatically scans your underlying instances and container images for vulnerabilities like unpatched libraries or exposed secrets. For real-time threat detection, deploy runtime security agents directly on the EC2 hosts. These tools monitor container behavior, flagging anomalies like crypto mining processes or unexpected shell access. Fargate simplifies runtime protection by eliminating host management, but you still need safeguards. First, scan task definitions for risky settings, like excessive IAM permissions or disabled logging. Since you can't install agents, lean on guard duty for ECS to detect malicious API calls or traffic to known threat IPs. Whether using EC2 or Fargate, enforce these rules. Enable ECS task definition no plaintext secrets to block unprotected credentials. Monitors task activity for suspicious process execution. Restrict IAM roles and network access. Rebuild and redeploy tasks frequently, never patch running containers. Amazon ECS provides robust deployment strategies designed for different scenarios. Rolling updates offer a straightforward approach by incrementally replacing older tasks with new ones, allowing your application to maintain capacity during the transition. This method works well for most standard updates where brief, partial outages are acceptable. For more critical production environments, blue-green deployments provide an extra layer of safety by running two identical environments simultaneously, your live, blue environment and a staging, green environment with the new version. Traffic is shifted only after the new version passes health checks, minimizing risk. Alternatively, canary deployments allow even finer control by gradually routing a small percentage of traffic to the new version, monitoring for errors before fully committing. To streamline these strategies, the ECS Deployment Controller automates the process, integrating with elastic load balancing to manage traffic shifts. If health checks detect failures in the new tasks, ECS automatically rolls back to the stable version, preventing widespread outages. For end-to-end automation, AWS Code Pipeline orchestrates the entire CI/CD workflow, building images, running tests, and executing deployments, while CloudWatch Container Insights provides real-time visibility into performance metrics during rollouts. By combining these tools, teams can achieve reliable, automated deployments that balance speed with stability. Whether you're iterating quickly in development or managing mission-critical production systems, ECS deployment features ensure updates happen smoothly, keeping your applications available and your users uninterrupted. When running containers on Amazon ECS, you have multiple storage choices to fit different needs. For persistent, high-performance block storage, Amazon EBS volumes are ideal. They attach directly to EC2 tasks, offering low-latency SSD or HDD storage, perfect for databases or cache-heavy apps. If you need shared file storage accessible across multiple tasks, Amazon EFS is the go-to solution, providing scalable, fully managed NFS storage that works seamlessly with both EC2 and Fargate tasks. Windows users can leverage Amazon FSx for Windows File Server, which delivers fully managed SMB-compatible storage optimized for Windows-based containers. For simpler use cases, Docker volumes let you manage ephemeral or persistent data directly through Docker's native volume system, while bind mounts allow containers to access specific directories from the host EC2 instance, great for development or temporary storage. Whether you need speed, shared access, or cross-task compatibility, ECS integrates with AWS storage services to keep your containerized apps running smoothly. Now that you have a solid understanding of ECS, it's time to put that knowledge into action. In the upcoming videos, we'll dive into hands-on practicals, guiding you step by step through real-world ECS deployments. By the end of this series, you'll be able to deploy a fully functional, 3-tier full-stack application on ECS with confidence. So, get ready to roll up your sleeves and start building. That wraps up this video. I hope you found it helpful. If you did, make sure to like this video and subscribe to the channel so you don't miss the upcoming hands-on tutorials. If you have any questions or thoughts, drop a comment below, and I'll be happy to help. Also, if you think this video could help others, don't forget to share it. Thanks for watching, and I'll see you in the next one.